Well, once again, good morning, everyone. Thank you once more for your punctuality and interest in this event. Let's now commence our second and final days of talks. Today, we are privileged to have two incredible presentations. The first by Dr. Elida Beatriz Armida, and second for Dr. Sanjaida. Following that, we'll engage in the knowledge quiz activity, encompassing all the talks presented this far. Once again, thank you for your presence, and I hope you truly enjoyed today's discussions.
And let's give our welcome to Dr. Elia Beatriz Hermida, who works at School of Science and Technology at the National University of San Martín, Buenos Aires, Argentina. She also contributes her experience to Bio3Lab, Laboratory of Biomaterial, Biomechanics, and Bioinstrumentation. Today, she will enlighten us on a crucial aspect of this field, the material utilized and the future challenges within this beautiful realm of knowledge.
Good morning, everybody. Could you listen me properly?
Yes, doctor, we'll listen you.
Okay. Thank you, the organizers of this International Symposium on Organ Bioprinting. I'll try to show you some of the advances we have been developing in Argentina and Buenos Aires regarding mainly aspects of material science related to bioprinting. We can just wait until the end of the presentations for some minutes for discussion, but any doubt you have regarding the concepts I'm going to show you, please don't hesitate to open the microphones and make a question, because this is a very interdisciplinary area, and sometimes we are talking using some words related to our specific area of work, and it's not going to be a problem if you just ask about this, let's say, a specific word regarding the presentation, okay? So let me share screen and you see if something works properly. Let's see this, now here. Let me see. Can you see the presentation now?
Yes, we can see the presentation.
Okay, thank you. So the title of the presentations are Biomaterials, Challenges for Bioprinting. And what are those challenges? They are coming from different aspects. Mainly, we are going to share with you those regarding the material science. And material science, why? Because we were talking about the scaffolds that are the structures that intend to emulate the extracellular matrix of the target tissue we are going to regenerate. And those scaffolds have different properties that are going to enhance the reconstruction of the specific tissue. So let's begin getting a deep insight into what kind of tissue we can regenerate. I can tell you that I began with this area around 2012, and at that time, the situation worldwide regarding the market by segments of tissues is the one that you see in the left column. The most important is the green area, and the green area refers to orthopedics, musculoskeletal, or spine tissues. And at that time, we also had the prospect that in 2018, 6 years after, they were going to enhance all those areas. So we say, okay, if we want to develop scaffolds for orthopedics, we can think, for instance, in what happens if we want to regenerate a bone. And the design criteria for bone tissue engineering, we can divide it into 3 scales. Let's begin, let me see with a pointer here. Let's begin with the macro scale. The macro scale is the one that we think when we consider the mechanical strength, so mechanical resistance of the scaffold we intend to use for the functional, let's say, development of the bone, and then also the geometry and the specific defects structures. Mainly, if we just move to the macro scale, the porosity, both in density of pores and also the pore sizes, the cellular infiltration is going to be related with the pores, and also the vascularization of the tissue. And finally, we also have to think, and any of these is less important, both the macro, the micro, and the nanoscale are important. And when we talk about the nanoscale, we are talking about the chemical composition. For instance, if we move here to this other picture B, we see that at the nanoscale, we are talking about the chemical composition in the sense that in bone, we have, for instance, collagen fibers, and also the mineral part of the bone, hydroxyapatite. And hydroxyapatite is a molecule made of calcium, phosphorus. So if we intend to allow the osteoblast to have a faster production of hydroxyapatite, then our scaffold should include materials, inorganic materials with calcium and phosphorus. For instance, 3-calcium phosphate, bioglasses, mainly with this composition. So also biocompatibility, we have to take into account. We need to use atoms and molecules that are going to enhance the biodegradation and the biocompatibility. This is one aspect, and it's not only restricted to bone tissue. Another example, if we intend to regenerate cartilage, we have to think in the scaffolds and also the cells we are going to seed onto the scaffolds or directly into the scaffolds, depending on the procedure we use to create that scaffold. And also signaling molecules. If we think about the materials, we can consider natural materials such as collagen, chitosan, hyaluronic acid, alginate, synthetic materials, or even a composite, a mixture of both between synthetic biodegradable materials, mainly polymers. We are talking about polylactic acid, polylactic glycolic, or also injectable hydrogels. When we think about cells, we have the chondrocyte. We also think about cells from the own patient, in the sense that in that way we are going to reduce any incompatibility between cells. So directly we are talking about scaffold seeded or created with cells from the own patient. But those cells could be chondrocytes or stem cells. Even stem cells can be adult mesenchymal cells or pluripotent or embryonic cells. And then we also can include signaling molecules. So it's a complex panorama we have to take care. And now let me just focus on the material science, on the mechanical properties and on the structure of the materials we are going to consider to create those scaffolds. Let's see what happens with the stiffness, the rigidity of the tissues we have in our body. There is a very large scale. The elastic modulus of a material is measured in a unit that is called Pascal. Pascal is Newton over meter square. This unit, if you see, if we are talking about a neuron or lungs, we have just 100 of pascals. But if we move through our body, endothelial cells, fibroblasts, smooth muscle, chondrocytes, osteoblasts, bone, we are moving towards gigapascals. So it's a very large scale. And in this very large scale, we are going to use different kinds of materials. We are talking about, in this presentation, we are talking about polymers, biodegradable polymers, and not only biodegradable, but also resorbable polymers. That means that they are degraded by or hydrolysis or enzymatic uh, attack by enzymes from our body. And this reduction, this degradation changes our macromolecules into smaller molecules that are not toxic to our bodies. In that sense, we are talking about resorbable polymers. So one of the points to take care of is that we have to use materials with elastic mechanical properties similar to those of the tissue we want to regenerate. Another thing that is very important, not only mechanical properties matters, also microstructure matters. This is one of example that we developed in our lab based on this work by Antoine et al. We made the polymerization of collagen 1 in PBS and also with some sodium hydroxide at two temperatures, 21 degrees, and then another experiment at 37 degrees. The concentration of collagen in both samples is the same. However, you see that the microstructure is different. We made measurements of the width of the fibers, and at 21 degrees, the fibers are thicker than at 37. And also we measure here, this is measurements of the elastic moduli as a function of time. And as the polymerization proceeds, you see here the blue line corresponds to the elastic part of the modulus, and it's around 100 pascals. However, when the fibers are thinner, it only goes up to 10 pascals. What happens when we put cells, fibroblasts in this case, onto these kind of structures? First, the behavior of the cells depends on the structure, the macrostructure, in the sense that here are only 2D, just surfaces onto, let's say, glasses. And here are real foams, 3D foams. So the behavior of cells, not only in addition, but also in proliferation, depends if it's 2D or 3D. In 3D, the cells are more relaxed and their addition and proliferation is faster. And also the behavior depends on the thickness. When the sample has thinner fibers, that is when it's not so elastic, when it's less elastic, then the proliferation is faster. So what we have to think is not only mechanical properties, but also microstructure. Let's see one of the challenges we have at the lab. We intend to reproduce, we are trying to reproduce a trachea, because in some instances the damage or even the congenital situation of the trachea with defects cannot be solved with anastomosis, for instance. So what happens if we intend to create a structure that allows the regeneration of the trachea? Trachea, we can say, like an organ. It's not just tissue. We have the cartilage, open rings. Also, we have the connective tissue between the rings. And also we have a small muscle here that is the one with large deformations that allows the movement of the trachea. How can we work with 3 different types of scaffolds? We can, or we have to produce, let's say better, we have to produce a complex scaffold with 3 different kinds of structures, microstructures, or even materials. Let's begin with one part. When we have a problem that is a complex problem, sometimes we cannot divide it in parts and solve it each one per its side and then put together the solutions. But we have to think more like what we have with an onion, just by shells. No? We take the whole problem, we intend to propose a solution, and then we see if this solution allows or not to solve the problem, and then we made changes to the whole situation. But in this case, we intend to separate the complex structure in parts and to see first how we can produce a suitable scaffold for the rings of the trachea. In order to advance with this objective, we consider this bioprinter, that is the bioprinter 3D donor version 3, produced by the Argentine company Life C. This bioprinter has 2 cartridges. One cartridge uses a syringe and the other one also a syringe, but with an envelope here that is like a heater that can allow to increase the temperature of the ink up to 40 degrees centigrade. The production, the printing technology we are using in this case, you have different kinds of bioprinting technologies. We are going to work with an ink that through pneumatic or mechanical extrusion through the needle leads to an extruded filaments, and with this kind of procedure, we are going to recreate the scaffold for the C structure of the cartilage of the trachea. What are the, let's say, the restrictions or the conditions that we have to consider for our ink? Let's see, this is the situation. On one side, we have to think, this is in the vertical axis, about the shape fidelity. We intend to print a C structure with a certain porosity. So what is our goal is to print with a very proper fidelity, not like this, that directly you have no structure at all, but real a structure of channels and layers with according to the model we have designed. At the same time, on the horizontal axis, we have an increase in polymer concentration, cross-link density, and stiffness. Of course, when we have a higher cross-link density, that is when the macromolecules of the polymers are really interchanged or entangled, then we have a better shape fidelity. However, as the polymer concentration increases, we can say also that the presence of water in our sample reduces, so it's not so easy for cells to adhere, proliferate, grow, and proliferate. So for cell culture, the better situation is an hydrogel with low concentration of polymers. So this is better for cell culture. This area with strong concentration and good shape fidelity is better for fabrication. And usually the traditional biofabrication window is here. And we intend to move with novel strategies here. Both will intend good shape fidelity and also proper environment for cell culture. What kind of hydrogels can we use? We have a very large list of different hydrogels. Some of them had advantages and also disadvantages. So usually our hydrogel is not, oh, sorry, this is in Spanish, but you can understand, of course. You can not only see what happens with one material, but usually our hydrogels have a mixture or blend, let's say, of different materials. For instance, we are working nowadays with a mixture of alginate, that is a material with a mild cross-linking condition through the incorporation of calcium ions. It has a very high biocompatibility, but poor cell addition. Since it had poor cell addition, then we mix with a little part of hyaluronic acid. Hyaluronic acid promotes cell proliferation, but has poor stability. However, alginate with the mild cross-linking provides stability, and also we add part of gelatin with also high biocompatibility and good thermally reversible gelation. Not only we can cross-link with chemical unions between the macromolecules, but also we can use the property of the transition between solution, and gel. What is the transition sol-gel? The sol-gel transition in gelatin depends on the characteristic of the macromolecules, because when I say alginate or gelatin, I'm talking about a chemical composition of the monomer that takes part of the macromolecules, but then I have also to inform what is the mean molecular weight, because the molecular weight strongly depends or it strongly affects the mechanical properties, the degradation time. So we have to give different characteristics of the macromolecules we are using in our hydrogel. Let's see what happened in the syringe if we intend not only to make an ink, but really a bio ink. That is an ink made of the hydrogel, a high amount of, I'm going to say water, but it's not water, but PBS or the system proper for the development and growth of the cells. What happens if we have those cells in a good environment, here in the syringe at the left, without any stresses, but then we begin to pull the syringe, that's the plug into the syringe, and then what happens? As you see here in this plot, we have U is a measure of the velocity, the speed into the fluid. And as you see, the fluid in the center moves faster than the one directly onto the walls of the syringe due to the surface tension. This difference in the velocity traduces into an increased stress tension from the center to the walls. So what happens? If you have here the cell, then onto the cells you have different shear stresses. And those shear stresses can affect the cells in such a way that they can also kill the cells. As you see here, the ones in the middle with virtually no stresses are those in green. Then there are some ones in orange that are rather stressed, but others onto the walls directly die due to the high shear stresses. How can we reduce the stresses? We can reduce the velocity or the force onto the flange of the syringe, but also we can reduce the viscosity of the hydrogel. But if we reduce too much the viscosity, then we are not going to have a good shape fidelity. So it's a compromise between good shape fidelity and the life of the cells. Therefore, we have to measure in the lab the shear stresses, both in the fluids when this is in a solid structure or in the gel structure, more like a solid. We measure the forces, we measure the areas. Of course, as the area increases, the force increases in order to have the same deflection. So what is the more important parameter is what is called the shear stress, that is the relation between the force applied to a certain area. And also we have to measure the deformation, that is called here the shear deformation or the shear strain, and also the velocity of this deformation. What is the shear velocity? We have different devices. This is called a DMA, Dynamic Mechanical Analyzer, to measure solids. And also we have other systems that I'm going to show you just in a minute. That is a rheometer to measure in the liquid form, the system. But let's go back to our bioprinter. We can put here a syringe and measure here in the syringe with a system we included in the lab that is a load cell, how to measure the force we are doing onto the plunger. And then also in the plunger, we have a scale to measure the velocity of the movement in such a way. And here we can put just one needle or multi-nozzle or multi-needle. And you see here, we can measure the force as a function of the time of extrusion. Here is when we have no liquid or no hydrogel, no ink into the syringe. This is the force we have to apply to move the plunger. And then what happens with the force when we have just one needle, and how we can reduce the force if we use multi-needles. So multi-needle is a very nice structure to accelerate printing, because instead of printing just a channel, we are printing 5, 10, 3, depends on how many nozzles we have in our system. And also we get good print fidelity and good viability of cells. This is we found more than 80% viability, between 80 and 90, if we print with 3 syringes, for instance. Let's go back to what happens with the characteristics of the hydrogel. So now what I'm trying to share with you is that trying to develop a proper bioink for bioprinting a certain scaffold for the tissue regeneration, we have different parameters to consider, and not only the composition of the ink, but also how we are going to print. So let's go back to the rheology. Rheology is the part of the material science devoted to characterize and study liquids or soft materials like gels. We can measure with this device. We have our sample here, for instance, the hydrogel or our cartilage sample, and we made small torsions in one side or the other, and in this oscillation way, we measure the deformation that is here in red, and also how is the stress or the torque of the motor required to follow this deformation. How much force the motor has to do to get this kind of deformation. Usually there is a shift between both signals, and this shift is related to the dissipation or the viscous structure of the material in such a way that we can measure the viscosity, that is the relationship between the stress and the velocity, the shear velocity of our sample. This eta is the viscosity. And also we can measure the modulus. What is called the storage modulus is the elastic part of the material, and what is called the loss modulus G2 primes is the, let's say, the viscous or the dissipative part of the behavior of the system. In any material, you have both parts. In metals or ceramics, the viscosity or the loss modulus is really negligible, but in polymers, both of them are important. So we have up to now composition, mechanical properties, what happens with the system we need to print or bioprint. There are also other parameters like the shear rate. If you say viscosity, there are some materials that has a viscosity that is independent of the velocity, the shear rate we use to move them. But there are many materials where you have this behavior, that is, as you move it faster, then the viscosity reduces. So you can have an hydrogel with cells, that is, you move the plunger faster, then the viscosity reduces, so cells are not going to suffer so much. So this is also important to characterize your structure before putting the cells and after with cells. As you see here, this is a sample made of simply gelatin in PBS at 37 degrees. It was printed with a nozzle just 100 micrometer thick, so a very fine structure. You can have here, this line is 250 microns. So you see here that you have pores around that value, 250 microns, and the lines lower than 100 micrometers because gelatin has shear thinning. So as you print, the faster the point that you are going to print is thinner than the diameter of the nozzle. This is a layer with, a scaffold with 5 layers. And we have here the modulus. It depends on temperature. As you see here, this is G prime. As you remember, this is the elastic part of the material, the elastic behavior. And this G2 prime is the liquid or the dissipative part of the material. At low temperatures, the behavior is more elastic than like a liquid. But at higher temperatures, above 33 degrees centigrade, the behavior changes. It's more liquid than a solid. So this here, you have at this point the transition from liquid at higher temperatures to solid at lower temperatures. This is what is called the transition salt gel or the gelation temperature. So this is another thing that is important. If I have the solution at 37 degrees, for instance, in the syringe, and the plate of the printer is at room temperature, then just when it's printed, it changes from liquid to solid. So cells do not suffer a lot because inside the syringe they are in liquid state. But when it's printed, since the plate of the bioprinter is at room temperature, then the structure remains with proper print fidelity. As you see here at the bottom, we have at, for instance, 17 degrees, the molecules are completely cross-linked. It's really strong how gelatin behaves. At 30 degrees is partially cross-linked, and at 37, there are no cross-linked, no engagement between cells at all. So as a summary, When we have the hydrogel, we have to take care of the chemical composition, the molecular weight, the concentration, the type of polymers we are using, since all these are going to impact on the viscosity, the gelation, temperature, the properties of the network related to the shape fidelity. Other parameters we have to consider are the nozzle gauge, the shear stresses we apply, the fabrication time. This is the same to say how fast we are going to move the planker. And all these parameters are going to impact in the printing fidelity and also in the cell's viability. Let me just show you other situations that can be related to the gelation. This is what happens if we are printing with a material under gelation. This is exactly at the point of gelation, and this is if it's over gelated. So if it's gel inside the syringe. So if we can control properly the temperature of the syringe, then we are going to have a structure with poor print fidelity or exact or very proper print fidelity. That is a parameter that can be measured just looking at the shape of the printed sample and comparing with the model. If it's 1, then it's exactly accordance between model and what we have printed. Also the overlapping, I'm not going to go into so details. So finally, if we are working with gelatin and alginate, for instance, we have here in our syringe molecules of alginate, gelatin, our cells. And if we print, just by changing the temperature, we can have a material just by gelation of gelatin with a moderate strength. So mechanical properties are not so proper, but with proper print fidelity. So once we have printed all our scaffold, we can put it into liquid with calcium ions, and then the alginate molecules finally also cross-link through the calcium ions. And we have here a mechanism to strengthen our scaffold. And also cells can live and move inside the hydrogel. In this case, what is important is to see how long does it take for calcium to penetrate into the scaffold. We have performed an experiment to see how fast can calcium ions move through the gel, cross-linking fully cross-linking the first part, and then here is the situation where things are going dynamically, and here is the gel that is uncross-linked. Why do we need to consider the time? Once is because we need to determine how long does it take to print a certain scaffold. But on the other side, for instance, if we print a cylinder and we immerse the cylinder in a solution with calcium, then the simulation says at 500 seconds, you have a thickness of 1 millimeter. And if I stop the cross-linking process here, and I stop just by removing the calcium and rinsing the structure to leave any other calcium ions, then we can also rinse the middle, and just by printing a cylinder, we can lead to a hollow structure like this. And this is very suitable in order to produce a scaffold to be seeded with cells and trying to get an artificial artery, for instance. Well, we talk more about this in one of our last publications. And just to end this talk and to leave some minutes for question, we can increase the complex situation of mixing polymers with any cross-linker and cells and print in different strategies. Let's say At the beginning, just one part of cross-linking, and then after being printed another, as I mentioned, with the gelation and then the cross-linking with calcium, also including more than 2 different kinds of inks. Here you have even one of the cartridges that has a heating unit for thermoplastics. Not only hydrogels, but we can also use certain kinds of thermoplastics. In this case was PCL, that is a thermoplastic that fuses at around 60 degrees centigrade. You can print really complex structure with more than one type of cells. So this is a very wide area of bioprintings. I wish to listen to you, and thank you very much for your attention.
Well, Dr. Armida, thank you very much for your incredible talk. We understand the importance and fundamental role of these science in improving many aspects of life. Now we'll open a 5-minute sessions for questions from the audience. Remember, you can type your question in the chat or unmute your microphone to ask them directly.
Yes, and also in case that some of you would like to ask the question in Spanish, please. I understand the idea to have the symposium in English, but please, I don't like to have English as a barrier for our interchange. Okay, thank you, Carolina, for your question. You see, I've been working in material science just since the last part of my activities as a student. I studied physics. So at the beginning, I worked with elastic materials, petrochemical polymers, not biopolymers. And when I began to work with biopolymers, the first area was trying to use biomaterials to reduce the impact on the environment due to petrochemical polymers. Just since 2010, I began to work in biomaterials. So biodegradable polymers to be used in our bodies. And the most fabulous work I've done was to talk to people of other disciplines. Because of that, I tried to show you the complexity of working with biomaterial from the material science area. Since I understood along this time that you have to know how people in other areas are working, not for working just like them. I'm not working as a doctor. I'm not going to do their work, but I need to understand how complex it is for a surgeon to consider a pediatric patient with a tracheobronchomalacia that needed a splint to solve that problem, and how he's going to work on a very small body to try to develop the better scaffold or splint in that case for him. So the idea is to get in knowledge to consider what the other professionals working in this very interesting topic are working to enhance the conversation and the work we have to develop together. That is one of the most interesting things I've developed along these years. Thank you for your question, Carolina.
Doctora, le hablo acá en español, que me escribieron en español. Me escribieron por privado que tenían una pregunta de que no, pues no recordaban bien, si a lo largo de su estudio sabe si es posible replicar todo tipo de tejidos, así como el cartílago de la tráquea, perdón, o existe alguna limitante que de momento no podamos replicar con este tipo de técnicas.
Okay. I should say that we have very low knowledge about the enormous complexity and the magnificent engineering work that nature has done in any of us. So we know really very little about tissues. And when we talk about an organ, no, the challenge of this symposium is organ bioprinting. We are really far from organ bioprinting, but the first things that we have to do in order to advance in order to get to our goal is to know the complexity, to get idea of the complexity, but not as to paralyze our work, but to really take into account that we have a lot to learn and a lot to know. And in that sense, I would say that we know really few percentage of the whole tissues in our body. But if you look at the publications, you see authors working on cornea, nervous tissue, of course, bone, skin, and cartilage are the most significant due to many things. One of them is that the life expectation increases, and what happens is that our body is not prepared for living so long. So you need to solve what happens with bones and cartilage and so on. But we have a lot to discuss and to work on different tissues. I would say that no more than 10% of what happens with the regeneration and the engineering of tissue is already known. Okay, interesting question. Is it possible to regenerate tissue that has been aged? More or less, that was the question. There are two different situations. One is to repair, and the other is to create a new tissue instead of the one that has been damaged. Both strategies are being used. I would say that I was going to use the word easier, I'm not sure if that's the best adjective to use, but I would say that it's easier, let me say in that way, to create a scaffold to regenerate a damaged tissue instead of repairing a damaged tissue. I'm not sure if I was clear in what I'm saying, but the idea is if you have a damaged tissue, it's better to remove and replace it, but scaffold that's going to enhance your body to solve the situation than try to repair.